Last chapter, fluid flow. Now, when we talk about fluids, we mean both liquids and gases. And the reason why fluids flow is because of pressure differences between 2 points. Fluids always flow from areas of high pressure to areas of low pressure. An example of fluid flow is blood flow in blood vessels. The understanding of fluid dynamics is very important and has been applied in various fields such as aerodynamics. A flowing fluid experiences internal friction called viscosity between the particles in its layers. While studying fluid flow here, we shall assume that the viscosity of any fluid is negligible and also that the liquids are incompressible. If all particles passing through any given point in a fluid have the same velocity, we call it a streamline or a steady flow. The particles trace the same path called the line of flow, which is represented by a line and an arrow. There is another type of flow called laminar flow. If you imagine a flowing fluid as having many lines of flow or layers, the flow is laminar if the particles in a given layer have the same velocity. And this velocity may be different from that of other particles in adjacent parallel layers. For example, you can see here that the particles appear to be overtaking each other, but even then, they don't cross each other's path. In other words, the layers do not mix. They are very distinct. The opposite of laminar flow is turbulent flow. Here, there is no orderly flow. The velocity of the particles is constantly changing, and the particles have no clear path that they are following. There are no distinct layers. Let us perform an experiment to determine how different shapes affect streamlines. We shall put different shapes on the path of a stream of smoke and see the overflow in front and behind the different shapes. A cube, a hollow sphere, and a teardrop. For the cube, we can see streamlines before hitting the solid, but are then broken into a disorderly flow behind the cube. In other words, there is a term in the pitch. We rotate the screw 5 times and record the distance moved by the main scale. In this case, it is 5 millimeters. The number of revolutions is equal to 5. So, pitch is equal to the distance moved by the thimble on the main scale over the number of revolutions. In this case, pitch is equal to 1 millimeter, streamline briefly, but eddy currents disrupt that, and a turbulent flow is set up a distance behind. For the teardrop, the streamline splits into 2 and flows over the outline of the solid and emerges behind it to join into a smooth streamline again. In this case, there is little to no resistance to airflow. This is called a streamline shape. This idea is used in designing vehicles with a streamline shape to cut through air with least resistance. The same thing applies to aeroplanes. The fish body is also streamlined and helps it cut through water with little resistance. The bird's body is also streamlined and helps it cut through air with little resistance. If you look at a section of the bird's wing from the side, you will see that it is big up front and tapers towards the back just like an aeroplane wing. When talking about flying, this shape is called an airfoil. The air flows around the wing in a smooth, streamlined manner. Next, the equation of continuity. Now, we can define the boundaries of a set of streamlines in a fluid flow. If the boundaries encompass a tubular region, then the resulting section is called a tube of flow. We shall use this tube of flow to determine the equation of continuity for a liquid that is incompressible, non-viscous, and flowing steadily. Fluid flow or flow rate is defined as the volume of fluid that moves past a certain point per unit time. Some books might call it volume flux. This is represented as Q is equal to V over T, where Q is flow rate, V is volume in cubic meters, and T is time in seconds. So flow rate is given in meter cube per second. Let's take a section of the tube at this point. Cross-section area is A1 and length is L1. So Q1 is equal to V1 over T. We know that volume is equal to cross-section area times height or length. So we have Q1 is equal to A1 L1 over T. If you think of this equation as Q1 is equal to A1 times L1 over T, L1 over T is the same as distance over time, which is equal to velocity. Then we shall have Q1 is equal to A1 times V1, where V1 is the velocity of the fluid along section 1. And so, flow rate at section 1 is given as the cross-section area of section 1 times the fluid velocity in this section. With an identical analysis, if we define a section 2 in the wider part of the tube, we will have Q2 is equal to A2 times V2. The volume of the fluid in section 1 must be equal to the volume of the fluid in section 2. And that is easy to see because no fluid gets lost along the tube length. And because A1 is less than A2, then L2 must be greater than L1. The key understanding here is that Q1 must be equal to Q2. And that means A1V1 is equal to A2V2. This is called the equation of continuity. You can think of it as a statement of continuity of flow or conservation of mass. That is, what passes through section 1 must pass through section 2 because volume is not created nor lost somewhere between the two. It therefore means area times velocity is a constant. And this constant is what we call flow rate. Let's take an example. Suppose we have a fire hydrant and we hook a hosepipe with a nozzle. The radius of the opening of the hydrant is 2 centimeters and the water is passing through it at a speed of 4 meters per second. The radius of the nozzle is 1 centimeter. What will be the velocity of the water as it exits the nozzle? The continuity equation A1V1 is equal to A2V2. Area is given by pi r squared. And so, pi r1 squared V1 is equal to pi r2 squared times V2. Substituting the values, the pi's cancel out. 2 centimeters squared times 4 meters per second is equal to 1 centimeter squared times V2. We divide both sides by 1 centimeter squared. So we shall have 4 centimeters squared times 4 meters per second over 1 centimeter squared is equal to V2. Centimeter squared cancel out and V2 is equal to 16 meters per second. Next, the Bernoulli's principle. Now, consider a horizontal tube AB with a connecting tube dipped in oil. The area of cross-section at C is much smaller than that at A and B. When water moves along the horizontal tube, its velocity increases at the constriction. This increased velocity results in decreased pressure below the atmospheric pressure, forcing the oil to rise up in the vertical tube. This speed-pressure relation is known as the Bernoulli's effect. It states that for a liquid that is non-viscous, incompressible, and with a streamlined flow, an increase in velocity produces a corresponding decrease in pressure. So, if you have a fluid flowing through a pipe with a constriction in it, in that constriction, the fluid will flow faster. To get through the constriction, the fluid must speed up as it enters the constriction, and as it leaves, it must slow down. And in order for it to slow down, there must again be a force applied, but this time in the opposite direction. The only possibility for a force to be applied is from the pressure within that fluid. That is, higher pressure in the larger section to make it speed up and then slow down. So, higher pressure in the flow direction on the left-hand side and opposite the flow direction on the right-hand side. This creates a low pressure in the constriction area. The Bernoulli's effect also applies in air. If you blew air over a sheet of paper, the high velocity of moving air creates a low pressure above it, causing the paper to rise. Again, consider a tennis ball traveling through air while spinning. It is observed that the ball assumes a curved path. If you threw a ball that was not spinning, as it moves, the air is going to move around it. But since it's not spinning, the velocity of wind at the top and bottom will be exactly the same. But if the ball is spinning, it generates a wind on the top, which counteracts the wind that is coming in, and that decreases the speed of the wind on the top. But at the bottom, since the wind over the ball and the wind generated by the spinning ball are both going in the same direction, the speed here is higher. So pressure is lower at the bottom, and therefore a force pushes the ball downwards. Next, the Bernoulli's equation. Now, in the continuity equation, we saw flow tubes of variable cross-sectional areas in which a non-compressible fluid was traveling left to right. And we said that the product of velocity and cross-sectional area on one segment must be equal to the product of the cross-sectional area and velocity on the other segment. For the Bernoulli's equation, we are not interested in the cross-section area anymore, but rather the velocities, pressure, and the height of the fluid above some arbitrary zero level. This is Bernoulli's equation. The pressure at point 1 plus a half times density times velocity at point 1 squared plus density times g times height at point 1 must be equal to the sum of these same values at point 2. In other words, the sum is a constant. This equation may look a little complicated until you realize that just like the continuity equation is nothing more than the conservation of mass, the Bernoulli's principle is a law of the conservation of mechanical energy applied to fluids. So, considering that kinetic energy is equal to a half mv squared, 10 the kinetic energy per unit volume will be given as m velocity squared over 2 times volume. But density is equal to mass over volume, and so kinetic energy per unit volume is equal to a half rho v squared. So this is kinetic energy per unit volume. Also, potential energy is equal to mgh, and so potential energy per unit volume will be equal to mgh over v. But density is mass over volume, and so potential energy per unit volume will be equal to rho gh, and so this is potential energy per unit volume. Let's look at an example of the applications of the Bernoulli's principle. We'll look at the Venturi meter first. It consists of a horizontal tube of varying cross-section with vertical tubes attached to the narrow and wide sections. A fluid moves along its length. The vertical height of the fluid in the constriction is lower due to low pressure as a result of higher velocity. Taking the height difference to be h and given A1, A2 and h, what will be V1 and V2? This is the Bernoulli's equation. The first thing is to realize that the vertical heights of the two sections, that is the wide and narrow sections, is the same, so these terms will cancel out. Rearranging the remaining terms, we shall have P1 minus P2 is equal to a half rho V2 squared minus a half rho V1 squared. Factorizing that, we shall get P1 minus P2 is equal to a half rho times V2 squared minus V1 squared. Applying the equation of continuity, A1 V1 is equal to A2 V2. Therefore, V2 will be equal to A1 V1 over A2. V2 squared is equal to A1 over A2 squared times V1 squared. And therefore, P1 minus P2 is equal to a half rho times A1 over A2 squared times V2 minus V1 squared. And that gives us a half rho V1 squared times A1 over A2 squared minus 1. From these, V1 and hence A1 V1 can be calculated. Next, we look at more applications of Bernoulli's principle. We start with the aerofoil. This is a structure that is constructed in such a way that the fluid flowing above it moves with a higher speed than that flowing below it. Aircraft wings and helicopter rotor blades are examples of aerofoils. Because the fluid flowing above the aerofoil has to travel a longer distance than that flowing below, it has to travel at a higher speed compared to the low speed underneath. The pressure at the top is therefore lower than that at the bottom, therefore creating a lift force. The pressure P1 is therefore greater than P2. The pressure difference P1 minus P2 gives rise to the lift of the aerofoil called the dynamic lift. The force of the lift is given by F is equal to P1 minus P2 times A, where A is the area of the aerofoil. Next is a Bunsen burner. Now, when gas is made to flow into the Bunsen burner from the gas cylinder, its velocity is increased when it passes through the nozzle. This decreases the pressure above the nozzle. Because of the atmospheric pressure outside the barrel, air is drawn in. The air and the gas then mix as they rise up, and when ignited, a flame is produced. Next is a spray gun. This is a spray gun. When the piston is moved forward, air is made to flow through the barrel, some of it going down tube A, and the remainder blowing past the mouth of tube B, where it causes low pressure. Because of increased pressure on the surface of the liquid and reduced pressure at the mouth of B, the liquid is compelled to move up to B and blown to the nozzle by the air from the barrel. The velocity of the liquid is increased as it passes through the nozzle because of the reduced cross-sectional area. The liquid thus emerges as a fine spray. Next is the carburetor. Now, due to the action of the engine pistons, air is drawn into the venturi. The fast-moving air causes low pressure above the petrol pipe. Petrol is drawn into the venturi due to low pressure in the venturi and atmospheric pressure in the float chamber. The mixture of air and petrol is thus drawn into the cylinders for combustion. Finally, we look at the hazards of the Bernoulli's effect. Now, the air flowing over a rooftop has a high velocity compared to the one flowing underneath. Consequently, the pressure acting on the roof from underneath will be higher than that acting from above. Therefore, the roof may be blown off.